Lab Report 3, The Work-Energy Theorem with Springs, by Alexa Muthel, Lindsay Royer, and Alexa Singh-Madger. The question we were trying to analyze was how does the work being done by a spring on an IO lab change with different spring constants and configurations? We hypothesized that since the amount of work is directly related to the changing velocity of the spring, as kinetic energy is dependent on velocity, the spring that experiences the greatest change in velocity would be performing the most work. This would correlate with a setup of a single spring, and the less stiff spring would accomplish this. As the green spring in our experiment was the least stiff of the two different kinds that we used, this spring should perform the most work. Our experimental setup is pictured on the left. We attached a spring to an IO lab and tied the spring side to the table and an IO lab side to a 100-gram mass to drop off the side of the table. Each of our 6 trials featured a different configuration of the spring. As we are measuring the different amounts of work done by a spring on the IO lab, changing the spring setup changes the physical characteristics of the spring setup and thus how it performs work. The IO lab took data on force, position, and velocity. We could be confident in our results due to the recalibrating the IO lab before taking data, re-zeroing it before each trial, and using general consistency in the way each trial was performed. Still, a source of error could be identified in the fact that the force sensor and the wheel sensor, responsible for position and velocity measurements of the IO lab, are independent of one another. Thus, the data collected from each could be slightly delayed or off from one another, thereby affecting the calculated amount of work. As a result, an experiment that could control for this by incorporating the use of an integrated force and wheel sensor would be a major improvement in the experiment. For our models, we constructed a free body diagram, a system schema, and energy pie charts. First, by observing our system schema, you can see that the IO lab is the only thing in the system because work is being done on it. The free body diagram shows the normal force, which is perpendicular from the surface, the gravitational force going down, the force from the spring to the left, and the tension force from the weight on the string to the right. Frictional force was ignored as it was assumed that the wheels had minimal friction acting on them. We diagrammed the energy pie chart starting from when the spring was fully stretched, where the kinetic energy is the highest, and as it went back down to its compressed form, the kinetic energy decreased. As for physical factors that we are and aren't considering, we are assuming that the springs are not overstretched but working at normal capacity. Otherwise, it would make it difficult to make a conclusion about the 2 red springs in parallel, for example, if the springs were not the same.
Some underlying physics about our experiment include the work-energy theorem, which is the work done by all of the forces on an object that causes an equal change in the kinetic energy of the object. Also, Hooke's law is the force needed to extend or compress a spring is correlated to the extension of the spring. The change in the kinetic energy was calculated from the recorded velocity values from each trial. The initial velocity was the maximum velocity caused by the weight pulling on the spring after being dropped. The final velocity was the 0 point before the cart began to move opposite the original direction of motion. This was also the maximum stretch of the spring. This area encompasses the negative work done by the spring to slow the cart down to 0 velocity. Work was calculated from plotting force versus displacement and finding the area under the curve by integrating the trend line between the force values taken at the initial and final velocities. Through the work-energy theorem, these values for each trial respectively should be equivalent. At the right is a graph from the second trial.
Unfortunately, none of the trials accurately showed the work-energy relationship. The work values were all greater than the change in kinetic energy. This discrepancy is likely due to the force sensor and the wheel sensor being independent of each other in their measurements. Trial 3 was also an anomaly in that the force measurements did not follow the expected pattern of increasing in the negative direction. This is likely an experimental error in the execution of that trial and not a result of the spring configuration, as that error did not occur with the other series trial. We found that the least stiff spring did the most work as per our hypothesis. Both the trials involving just the green spring did the most work. Both trials involving just the red spring did the second most work. Trial 4 did the least amount of work because the combination of the springs in parallel prevented the IO lab from moving as far. This trial also correlated with the least amount of change in kinetic energy as it should. However, it would make more sense that trial 6 had the least amount of work done as the red spring was more stiff. This was not what the data showed, so either this is an experimental error or there is other underlying physics going on. One application of why it's important to consider the stiffness and configuration of springs is mechanical advantage. Springs are used in many everyday objects such as screen doors, appliance doors like ovens or toaster ovens, couches, and mattresses. It would make sense from an engineering perspective to maximize the amount of work done with minimal effort put in. Our data shows that a less stiff spring performs the most work. This would be useful when you need to use a spring that would stretch far easily. But less stiff springs would be more likely to stretch past their breaking point, so this is only useful to a certain degree. In conclusion, the green spring did the most work, whether it was on its own or in series with itself. This is likely because of the 2 springs, the green had a smaller spring constant and it was more stretchy. This correlates with our original hypothesis that the less stiff spring would perform the most work. The discrepancy in change in kinetic energy measurements and work measurements is likely due to the separation of the wheel and force sensors. Further experiments could include testing springs with more varied spring constants to further explore the nature mechanical advantage, and also executing multiple trials with the same spring configuration to ensure consistent results.